Hello all and welcome back. So in this video, let us continue our discussion on quicksort, and now let's write a workable code for the same. Pretty sure that you have tried the same out once at your end. If not, a humble request to do the same. Even if not fully, you will be able to get 70-80% gist of it, and the rest will get cleared in this video. Okay, so now let's get started. For the simplicity, just for this particular case, I'm just removing this extra 4. Again, that should not be a problem. I will be taking that towards the end as well. What I'm gonna do is basically, let me just copy this into a different file so that you can like code on that once you get this file. What I'm going to do, everyone, here is first let me actually work on this partition function, because actually if I see, this is the main function here, right? Partition function is where all the work is happening. Nowhere, like this is the major, just like in merge sort when the merge function was there, here the same thing is happening in the partition function. Okay, so let me just go a little bit deep into this and explain you the same. Now the very first thing is I'm getting this S and E here, right? I can like what I have to do is I have to take a pivot here. And I have to make sure that I am bringing it to its right position. Okay, just one more thing, which is the most common thing where we make mistake, where I used to make a lot of mistake. We have to always consider this as a part of some array. Okay, that's why we are dealing in terms of S and E. Okay, so now the next part is to make sure that I'm able to bring this 5 to its right position. For that, what I can do is I have to start. Okay, so just let me remove this. Yeah, 1 second. Yeah, so let's say my I initially is S and I'm taking one right position. Okay, I'm taking one right position also equal to S. Now, so just to make it a little bit more easy, I is here and my right position is also here. Okay, 1 second, let me just use one of the more feature. Notes layers, second here. Great. 1 second. Okay, no, second everyone. Should be fine. I was just trying to use another feature, but seems like that is a little bit complex. But anyways, everyone, just pay attention. So we have this right index, okay, right position, sorry, here as well. So my understanding here is that I'm going to start and assume that, okay, it should come in the starting. I'm going to count how many elements are there which are smaller. And if it is smaller, then I'm going to just like increment this right position. Okay, so pay attention, everyone. This is my right position, right? First is I. Element at I, which is 3, less than my pivot, seems so. So what I'm going to do, I'm going to move my RP here. Let me make a different color pen. I'm going to move my RP here. Okay, and I will be increasing at each and every point. Now, is my 6 greater than pivot? No, it's not. So I'm not going to move my right position. I'm just going to move my I. Similarly, is my 7 greater than pivot, which is 5? No. So not going to move I. So you're not going to move RP, I is going to the next. Is my 2 less than 5? Yes, seems so. So let me move it again. So what I'm doing effectively here is I'm making space for all the elements which are smaller than me using this right position index, right position variable. Now, similarly, is this 1 less than my 5? Yes, it is. So let me move it here. Okay. And finally, is the 4 less than my 5? Yes, less than pivot index. So I'm going to move RP again. Okay. And if you will see now, this is where 5 should come. Why is that? Because I have just started from the S, basically from the start of my array, gone till n minus 1, basically just before pivot. I've gone till n minus 1 just before pivot. Okay. So all these I have covered, and I have just allotted space for all the elements which are smaller than me. Okay. Such that I know that, okay, right now 4 elements are smaller than me, so I need these 4 spaces. Okay, just let it remove. These 4 spaces I need, and my RP is actually now at the right position. Will request you to see this once again, okay, if it is not clear. But that's how we can get the position very nicely. You can also count the same. You can count, let's say, how many elements are smaller, and then do S plus C as well. Okay, that is also going to work fine. But if you will see, I'm just incrementing it by every time, and just that is how S plus C is going to get calculated as well. Okay, so this 5 is now should come here. Okay, so let me do this, everyone. So let me now just start coding in this partition function. The first thing is I have to define my pivot. pivot I take L1 of E, right? Once my pivot is defined, I have to define I is equals to S and right position. Let me take in right position only so that your code is pretty nice for you all to refer. Right position. Now what I'm going to say is while my I, okay, while my I is less than equal to E minus 1. Okay, so you can write less than E as well. Pretty sure by like by now these things are clear, but I tend to make sure that the boundaries are very well defined. Okay, if this is the case, then what I have to do is if my L1 of I is less than pivot, if it is less than pivot, I just have to do right position plus equals 1. So I'm just increasing my right position if that's the case. And in any case, I is going to get increased at every step, right? Because I'm going to each element using I. Once this is done, I actually have the right position where my 5 should be. Okay, so as of now, my 5 is here, everyone. My 5 is here, but I have to bring it here. So what I have to do now? All I have to do here is bring my 5 here. Okay, so I just have to swap them and 1 here. So this is what's going to happen. 4, 3, 6, 7 and 2, right? So just this, if I do, I will be bringing my 5 to the right position. And you can see that in left, 4 spaces are there, which are the 4 elements smaller than 5. In the right, 2 spaces are there, 2 elements bigger than 5. Okay. So something which I have already explained in the last video, just want to make sure that you also grasp for how you have to write the code. That is how you have to understand it. One thing more, please follow the framework. Don't try to get a lot more depth into the tree, like exactly how it's going to happen or anything. Just solve for the cases the way we have understood it. Now, once I have actually got this, what I have to do, L1 of right position, okay, and L1 of end, okay. This is something which I have to swap. So the right position is going to go to end. So what I'm saying is that this 1, it should go to 5 and 5 should come to my right position, right? So 5 should come to right position. 1 second, yeah. I hope this works fine as well. So all I'm doing is just swapping here. So just move the end to the right position and right position पे जो element, the element which is at right position to that to end. Okay, cool everyone. So yeah, now once this is done, okay, I think I also have my pivot index, something which I have to return, which is nothing but right index, right? Right position, sorry, my bad, right position. So this is actually the index, right? So if you will see in the last class where I explained you what we have to return. So this pivot index, okay, it is something which my partition function returns. And I have actually got my pivot index from via this particular code. Now the work is half done. Still. Okay. So what I have to do now, make sure that everything smaller than pivot to left and greater to right. Okay. So the work is half done as of now. That is not something which I have to do. Now again, let me do something. So start is going to be at S and my end is going to be at E. Okay. Now see what I'm going to do. I'm going to say that, hey, while my start is less than pivot index. Okay. So while my start is less than pivot index and my end is greater than pivot index. So now what all I'm doing is just trying to make sure that I squeeze these boundaries. So this is my start and this is my end, right? This is my pivot index. I have to make sure that, you know, everything towards the left, which is this part, okay, that is less, and everything towards the right, which is this part, that is more. Okay. So with that in mind, what I'm going to do, I'm going to start and compare. If at start the element is smaller, seems right, okay, I can move forward. But once I move forward and go to 6, then I think there's a problem. 6 is not smaller than 5, so we have to do something. We must somehow push it backwards. Similarly, if my end, it is not bigger, then also we have to do something. And yes, we have to then now just swap both of them. Okay, so let me just do this in code as well, so it is a lot clearer, everyone. Pay attention. If my L1 of start, okay, is less than pivot, then I have to just do start plus equals 1, right? Else if L1 of end is greater than or equal to pivot, then all I have to do is end minus 1. Now you will actually just understand one thing here, that while I was trying to shift it to the right position, I didn't consider equal to here, okay? And that's the same reason I'm not now considering equal to here as well. Whenever you are doing such kind of question, always have a practice of like fixing where you are going to put this equal to, okay? So because I have not put equal to here, I was considering everything which is equal greater than my pivot. Similar thing I have to do here as well. If that is not the case, if both the cases are like, if everything is like, let's say both these statement fails, then what I have to do, everyone? Then I just have to swap these elements, right? So L1 of end is equals to L1 of end and L1 of start. Once I've done this, start plus equals 1 and end minus equals 1. And yeah, I think this is what all we should do, and we should be good to return the pivot index. Okay. So just one thing, I will explain you this a little bit more better. So let me just draw here only, and let me see what was our array. 3, 6, 7, 1 second, 3, 6, 7, 2, 5, 4, 1, right? So pay attention everyone. 3, 6, 7, 2, 5, 4, 1, 4, 1. What I'm saying is my start is here and end is here. So I'm making sure that I'm calling it start and end. You can use them I or J as well. That should be fine. But just make sure that you're not messing this S and E up. Okay. So that in worst case, we have to use them afterwards. These functional arguments should be as it is. Okay. Now this is my pivot. This is my main index. If it is smaller, S can move forward, not a problem. Okay. Then I'm checking again for S. Then I'm checking again for X here. It is not smaller, so I will go to E. This is also not the case. E is bigger. Now actually I will swap them. Okay, so I will swap them. So it will become 1. It will become 6. This is what will happen when we swap them. And I'm going to move my S and E as well. Now in this case as well, if you will see, my S basically, okay, this particular element is not less than, it's not less than my pivot. Similarly, E is not less than this, okay. And now what I have to do? Again, I will swap it. So this will come, 4 will come here, 7 will come here. It's going to be S and it's going to be E. Now one thing here, we don't have to actually check after this our code will run. The reason for that is, if one of the start or end pointer is able to reach to pivot index, then that means that all the elements at that particular side is greater or smaller, right? Because what I'm saying is that, let's say if E starts from here and it's able to reach to my pivot index, then that means that everything is smaller here. And if everything is, if everything is larger here, and if everything is larger here, then for sure I can say that everything is going to be smaller here, because I have counted my positions and then moved my pivot. I have counted my position and then moved my pivot. Okay. So that's the reason we are not running these loops again the way we are doing in merge sort, because we are sure that, hey, if my end is able to reach, I know that, okay, it has just 2 positions or 5 positions which are right for this particular case. If I'm able to do that, I should be all good, and thus I can move for the same. Okay. So cool everyone. I hope with this it is clear. Let us run the same as well to see if it is working or not. So pretty big code we have written for this, but yeah, I will just suggest to write these codes in the initial manner with good names and everything, so that you're able to understand the same as well. Now quick sort, yeah, we are calling, and let me just run it. Nice. Seems that our code is working because we are able to get it in sorted manner. Let me now add another 4 as well. Should not be any problem because we have handled this properly. Okay. And if I run it, you are able to see 1, 2, 3, 4, 4, 5, 6. Okay. So yeah, with that, I hope you're able to understand the same as well, everyone. Now, one thing more I would like to show, same thing which I showed you in merge sort, the way we have actually understood recursion and the way you are writing a partition function, you can actually test it individually as well. Okay. You can test it individually as well. How you can do that? Pay attention everyone. So let's say, I have this L1, which is like this only. Now I have this partition function I'm calling L1 0 and length of L1 minus 1, right? And I'm printing L1 here. For the timing, let me just comment everything down. And see, the understanding is, if I've written my partition function correctly, this 4, let me make it 5 as of now, because this is what you understood it on. This 5 should reach at its right position, and all the things on the left should be smaller, all the things on the right should be bigger. That is what our understanding with partition function is, right? Now this thing of course will be a lot helpful. Let's say you are not able to write this particular code, just check your partition function separately, because everything lies there only. Why you should go on recursion and everything? That is some smart work that you can do in your OAs or in your interview or anything, which an interviewer will also basically appreciate, because you are able to break your problem in smaller problems, the way recursion does. But yeah, okay. Now if I run it and you see the output, okay, let me show you that output to you. See, I think it has done its work. 5 is at its position, 5 is at the position we wanted, and everything on the right is greater, everything on the left is smaller. Yes, they are not sorted as of now, but that was not my work even. This part and this part, recursion and quicksort will handle. I don't have to worry on that. Okay. So again, this is very, very important stuff, everyone. Please make sure that you understand and see that, okay, for which question you can test like that, and you will be saving lots of your time. Okay. So now let me just do one more thing. Let me just try to showcase you this using a visualizer as well. Again, this will be a little different from our case, because we take, one second, yeah, let me run it. Great. So one more second, let me take erase only, that should be fine. It's 7 length, yeah, cool. So pay attention, everyone. What happens is that it's not going to take the pivot in the end. As I said in the very starting to you, that pivot you can take any element. Like you can take the starting index, you can take the end index, you can even take any randomly as well. So what it's going to do is it starts a pivot randomly, then move it towards the end, okay, then move to the end, and then it works basically on the same principle. So now it's the 2 pointers are here. Okay, let me just zoom in a little bit. So now these are the 2 pointers. Okay, what it's going to do, let us see. The overall, I would say, implementation might be a little different, but let us understand. Move to the left bound to right until it reaches the value greater than or equal to the pivot. Okay, so we are just trying to move this left. Let us move it. Okay, so it's saying that, okay, 3 is the biggest one. So it's going to count. Like this is also another way it's counting, just nothing else. Okay, so it's saying that, okay, this is as far as we can go, and it's just shifting it. Okay, somehow it is like doing things, but I hope you're able to understand. This implementation is a little different from what we have done, but overall it will try that it is able to find the right position for pivot, and that is what it is doing directly here. So it is just trying to actually see, okay, where the pivot should be, and based on that, so pivot it move to the end, and finally after some time it's going to move your pivot to 2 points. See, pivot is brought to the right position. Now the next part, okay, left sublist contain a single element, which means it's sorted. So this is our base case, which is going to handle here, and now it's going to call the same problem, the same thing on the right sublist. Okay, I hope you are able to understand this, everyone. Because the 2 was selected as a pivot, it took to the end. We can just ignore like how it did the other part. That should be fine. It brought to its right position. Now it's calling the quick sort on the left part. Okay, and I hope you all also remember that how we draw the tree in terms of Fibonacci, where yes, the left part always is going to get first solve. Now because it's a single element, S will be equal to E. And because S is equals to E, we are going to just return. So that's what it's saying. Left sublist contain a single element, which means it's sorted. If it is sorted, then we are just call on the second part. And pay attention now. Call quick sort on the right sublist. Once I call it on the right sublist, it's selecting this 3. For this 3, it's going to move to the end. So see, it's moved to the end. Now it's going to find, like, do the partition. Okay, so partition it might be doing in some different manner. That should not be a problem. Our implementation is more than good. We have understood it intuitively. I've explained you that exactly using that school example, and I hope you always remember the same. So don't get confused. Of course, there can be more than one way of doing any particular problem, right? So it's going to do the partition. Okay, move the left bound to the right until it reaches a value greater than or equal to the pivot. Okay, so it's saying that, okay, this is as far as it can go. Similarly, left it is trying to do to find the less value. It didn't find any less value. So I think these things are there. It's going to just send this pivot to the 3. Now again, left quick sort on the right sublist, because left nothing is there. Now when we call on the right sublist, again it selected a pivot which is 6. Gonna shift it, do some process through which it will be able to find the right position. Okay, once it finds this right position, it's gonna send 6 to this particular position. Okay, let us see. Yeah, 6 is on this position. Now 5 and 4 will come. 5 and 4 are gonna get sorted. Select the pivot as 5, shifted it to 4. Doing the partition, we don't know how it's going to do it, but I think it's fine. It is on the right position only. So if it's on the right position, okay, it's going to be here only. Pivot is moved to the final position, and now 4 and 7 are left. So it's going to call for 4. Okay, single element, it's going to get sorted. Similarly, write 7 single element, it's going to get sorted, and we have our own thing sorted. Okay. So yeah, with this, I took it a little quick because major steps were of the partition part, and I don't want to confuse you. So that's why I just showed you what exactly is happening. Right, the major of, I would say, in every iteration, 6-7 steps were of the partition problem, something which we have done differently. Okay, so I don't want to confuse you, and that's the reason I showed and basically just skipped through it. But I hope you get the idea after visualization that how things are moving forward. Here as well, it was doing the same thing, finding a pivot, moving it towards the end, then finding the right position to the pivot. The partition was a little different, but overall it was able to see that yes, I am able to finally move everything towards the left on the which is lower and on the right which is greater. Okay, so that was the whole aim and whole stuff which this particular problem did, everyone. Now same we have done here. I have also told you how you can check this particular code in middle. Okay, so this is a very helpful trick, I would say. Let's just comment it, and let me just comment this. Remove comment, yeah, and we can run this. 1 second. Yeah, so we are able to get this. And yeah, that is more than enough, I think, for quicksort. It is gonna work fine. So please make sure that you try to write it yourself as well. Again, it's a little bit difficult to grasp, but I hope with the intuition and with the understanding which I have given you, you are able to understand it, and now you will be good to write the same. If it takes time, please make sure that you're giving the time. Please make sure that you're drawing all these steps, even if you have to do all these 67 steps in the starting. Like let's say you're working it for the first time. Please make sure that you spend that time. Okay, don't worry on that. It's gonna take time in the starting, but as you code along a lot of recursion problems, it's going to become easy. Okay, cool then everyone, thanks a lot. So let's meet in the next video where we're going to start with recursion and strings. Thank you.